Our clocks and watches are set to civil time, which is designed to follow the sun. We call the average time between noon and noon one day, and divide that period into 24 equal hours. It takes roughly 365.25 days for the Earth to revolve around the sun. In order to keep the calendar in phase with the seasons, we add a leap day every fourth year. Civil time can be affected by daylight saving time in some countries. Civil time isn't very useful for astronomical work, but it is the version embedded most deeply into our brains because we use it every day. Time zones are based on the division of the world into 24 time zones of 15 degrees longitude each. The time convention begins with Universal Coordinated Time, UTC, which is also commonly referred to as Greenwich Mean Time, GMT, being located at the prime or Greenwich meridian. A time zone is one of the areas into which the world is divided where the time is calculated as being a particular number of hours behind or ahead of GMT. Trinidad is in time zone, UTC-4. Universal time is similar to civil time, but is more useful for astronomical purposes. Like civil time, it is based on the sun. There are 24 hours in a day. Universal time is never affected by daylight saving time. Universal time is defined at the prime meridian, or zero longitude, but is used by navigators worldwide. The information in the nautical almanac is calculated and reported in universal time, because UT has the same value everywhere. If a sun is due to rise at 6 o'clock UT, then navigators all over the world at different places on Earth can make different corrections to turn their local civil time into UT. In the 1700s, Harrison invented the marine chronometer, a long-sought timekeeping device to solve the problem of establishing your east/west position or longitude. Time is important because if your clock is off by 1 second, that means your longitude will be off by 0.29 miles, if you are at the equator. You also have to wind a spring-driven chronometer at about the same time each day, and listen to a time signal from the radio and record differences in the chronometer book. Time and navigation are inextricably linked together. Nowadays, we have satellite navigation to help us know where we are. These satellites contain several very precise and accurate clocks, because time and location are completely and totally interrelated in satellite navigation. The time difference between each degree of longitude is 4 minutes. So if it is 12:00 hours at the prime meridian or 0 degrees longitude, it would be 11:56 hours at 1 degree west longitude and so on. A navigator on a vessel in longitude 60 degrees west, off the east coast of Trinidad, plans to do an amplitude at sunrise. On the same day, another navigator on a vessel in longitude 61 degrees west, off the west coast of Trinidad, also plans to do an amplitude at sunrise. Both navigators go to the sunrise part of the nautical almanac and extract the time of sunrise for date and latitude. The sunrise time in the almanac is 0600 hours. The navigator on the east coast checks the conversion of arc to timetable in his tables, and finds that 60 degrees converts to 4 hours of time. The navigator on the west coast checks the conversion of arc to timetable in his tables, and finds that 61 degrees converts to 4 hours and 4 minutes of time. The navigator on the east coast applies the arc to time correction to find the UTC of sunrise that day, then converts the UTC to local time. This navigator will see the sunrise at 0600 hours. The navigator on the west coast applies the arc to time correction to find the UTC of sunrise that day, then converts the UTC to local time. This navigator will see the sun rise 4 minutes after his friend on the east coast, at 0604 hours. An azimuth can be taken at any time of day. It is restricted only by cloud cover. Because of the angle that we are calculating, azimuths would be more accurate when the body is lower. First, we take and note the bearing of the sun. We quickly note the accurate time of the bearing. We took the bearing at 0800 hours, and we were in longitude 60 degrees 30 minutes west. We convert the longitude to time, using the Arctic timetable in RIS, and apply it to the time of the bearing. The result is the time we have to find the GHF using the nautical almanac. We have to be careful with extracting GHF for bearings taken at night. If we took the bearing of the moon at 2200 hours on the 5th of the month, and we were in longitude 60 degrees 45 minutes west, we convert the longitude to time, using the Arctic timetable in RIS, and apply it to the time of the bearing. The result is the time we have to find the GHF using the nautical almanac. In this case, the time we look for will be 0203 hours on the 6th